All right, let's get going again. The second half of today's class could well be the most important half class in the whole quarter. So, well worth staying awake for. In this class, we're going to talk about overfitting in decision trees, but overfitting is not just a problem in decision trees. It's a problem in any powerful machine learning approach. So some of the issues here and some of the ways to deal with them are going to be quite general. Okay, so this is the first of many times we're going to encounter this. So first of all, let's see what the overfitting problem is. And then let's see how we can try to solve it or at least address it in the context of decision trees. Okay? So going back to our example of playing tennis, right? Let's suppose that, there was this one time when, it was a beautiful Saturday, a beautiful Sunday morning, let's say. It was sunny, it was not too hot, it was not too humid, not windy, not rainy. It was a perfect day for playing tennis. But your friend had been out partying the night before and had a huge hangover. So now she has a huge headache and she has in a bad mood. And when you call her back, if she wants to play tennis, she says no, absolutely not. Right? What does that do to your decision tree? This is the question. So, here's a more concrete example, right? Let's suppose that we had an example that was like this. It was sunny, right? So we go down this branch. It was hot, but we don't care about the temperature. And then the humidity was normal, right? Which means that the answer should have been yes. Right? Your friend should have been yeah, let's go and play tennis. But your friend said no. So now what happens to the decision tree? Exactly. I need to keep splitting here. This is not a leaf yet, right? I'm going to need to split on something more. And I can't split on something more until I get the answer that I want, which is no. Okay? So now your decision tree learner is happy, right? But what's the problem with this? What went wrong here?
The other side of the yes might be possible.
Yeah, the problem is that it wasn't because it was a bad day for playing tennis that your friend said no. It was because of a completely random thing that you have no power over and no ability to predict. So what I should have done is held off on that. So this example looks like an outlier. That's the technical term, outlier. Right? It really shouldn't be here. Instead of me trying to fit a little branch of the decision tree to this example, in the process now I get a whole bunch of others wrong, right? A bunch of things that should have been yeses now become no. Let me hold off on that. Okay? So the moral of the story here is if I try to fit my training data set perfectly, I will end up with something that may look very good, but is actually very bad. Okay? Everybody got the general idea? This is a crucial concept in machine learning. So let's generalize from this example, right? What is overfitting? Here's one way to define it. We're really concerned with two kinds of error. We're always going to be talking about these two kinds of error. When we do our experiments, when you guys do your projects, you need to distinguish between these two kinds of error. When you do the theory, it's all going to be about these two kinds of errors. These are the error on the training data. This is what you can see and optimize. How many of the training examples am I getting wrong? Right? How many users am I making the wrong prediction for on this clickstream data? Let's call this the error train of H. The other one is what you really care about. What you really care about is the error on the entire distribution of the data. It's the error that you would get if you could somehow see everybody. Get all the data that you're ever going to get in the future in very large, infinite amounts, let's say, and you knew exactly what the distribution was. That's the error that you want to optimize, right? Let's call that the error subscript curly d, where d is the distribution of the data, right? The whole problem in machine learning is that this is what we want, but this is what we have. If the two are the same, there would still be a complicated computational and optimization problem, but it would be no different from the problems in many other areas of computer science. The thing that's, pretty unusual about machine learning is that there's this disconnect between what you have and what you would like to have. Okay? So we're going to say that a hypothesis overfits when it looks like the best one on the training data, but on the test data, on the true distribution, on the data that you're going to see in the future, it's not the best hypothesis. So H overfits if there's some other hypothesis, H prime, such that the training error of H is lower than the training error of H prime, but on the test data, the opposite happens. The error of the other The error of this hypothesis is greater than the error of the other hypothesis. So I should really have picked the other one, yeah.
But you don't actually have the test data.
That's the problem. So the whole thing here, which seems like almost impossible perhaps at first, is like, I need to try to guess from the training data who is going to do better on the test data. And certainly, the training data is precious, right? That's what I have to go on. But I also need, so I need to be a good friend of the training data is one way to look at it, but not too friendly, right? If you get too friendly with the training data, you start forgetting about what you really care, which is the test data. So your training data is a guide to what happens on test data, but so you need to very much take into account. But it's an imperfect guide, so you also need to be, to hold off a little bit. Okay? It's a bit like playing golf, right? Then there's the first part of the swing where you're accelerating, but then there's the part where you have to stop, right? Otherwise, you won't have a good swing, right? We need to fit the data. That's the first part of the swing, and then we need to hold off. That's the second part. Both parts are essential for a good swing, and if you just have one of them, you don't get anywhere. Okay. Questions? Okay, so this is the theoretical definition. Let's look at overfitting in practice. These are the kinds of curves that people who do machine learning in practice look at all the time, and these are actually quite typical. So these curves here, can everybody see these two curves here? Okay. So this is actually on a real problem. This is diagnosing diabetes. This is actually a data set. It's publicly available. You can download it from the web and you can play with it. It's diabetes diagnosis. And we're building a decision tree to, based on a number of tests and symptoms, decide whether somebody has diabetes or not. Okay? And here's what happens as you increase the size of the tree. So as you add more nodes to the decision tree, right? So you're learning a bigger and bigger tree, right? Well, first of all, when you have, when you just predict the most frequent class, which is this person does not have diabetes, you get 65% accuracy. Okay, so this axis here is the accuracy. Okay, so just predicting the most frequent class, right? This is your, sanity strawman is what happens if I just predict the most frequent class? Do I do better than that? That gets you 65% accuracy. Okay, which is better than nothing, but not very impressive. But now, notice what happens as I start to grow my decision tree, right? The solid line is my training set accuracy, so my accuracy on the data that I'm seeing. And not surprisingly, it just goes up and up and up and up. It never goes down. Why does it never go down?
So splitting and we're going
by design, right? Whether my measure is error rate or information gain, if I'm optimizing that, the error can never be going down, right? Let's think of error rate, right? That's the simplest one, right? I picked this guy because it made the error rate smaller, right? If nothing makes the error rate smaller, I stop right there. Okay? So if you only looked at the training data, this is the mistake that rookies make, right? You say great. And now you may be laughing at the rookies, but I've had the experience in this class of somebody saying like, hey, we mined the clickstream data set and we got 100% accuracy, so why don't we have a better grade? And I'm like, you don't have a better grade because you got 100% accuracy. Right? It was 100% accuracy on the training data. And if you think, but that's okay, these are beginners, right? These are just students, right? You're here to make mistakes. Make them all here so you don't make them out there in the world, right? That's what education is for, right? But I remember, when I was a grad student, being in the office with my advisor, meeting with him. He was consulting for, various companies and institutions that need, machine learning. And I remember an exchange of the type, he asked them, like, so what are you using right now? And they said something like, I think it was a health problem, but it doesn't really matter, right? And he said, like, we're using a decision tree. But they wanted his help, right, for some reason. And then he asked them, so what is the accuracy of that decision tree? And it was like, oh, that's 100%. We're doing very well in that respect. Not a problem then, right? Yeah. So this happens. As a third example, right, I was an intern in a research lab once where they did a lot of speech recognition. Right? These are people who are very excellent researchers. They know what they're doing. Neural networks were hot at the time. They were using neural networks to do speech recognition. Right? Very natural fit, right? And they trained but these were the early days, right? So people didn't understand these issues very well. They trained a neural network that was just perfect. Actually, what they were doing was speech synthesis. They were doing speech synthesis. So you got in the text, right, and you had your neural network output what, the thing should be saying, right? This is a famous, neural network example, right? Because neural networks are very good at this. And so they train this on a whole bunch of sentences. Here's the text, here's the pronunciation, here's what you say, right? Here's the spoken sentence versus the text sentence, right? They train this on a sliding window, as is often done. The accuracy on the training data was perfect. And then they went and tried it on new data that they got from a telecoms company or something. And you know what came out when they actually ran the speech synthesizer with the neural network inside it on these new examples? For all of the new examples, what came out was white noise. That is overfitting for you. They got in the text sentence and out came shh. The neural network, and then they went and figured out what the heck had happened, right? What had happened? The neural network had exactly memorized all the training examples. It may not be obvious in a neural network how you do that, right? But if I can actually tell you in more detail I won't here, but it has enough power if you give enough neurons enough weights to just memorize the training data. It was massively overfit. Okay? So the same thing is happening here. Look at what's happening here. On the training data, things get better and better and better and better. But let's look at what's happening on holdout data. Right? This is what you should always do when you're doing machine learning, is don't do all your trying things out and whatnot on all the data. Because if you do that, then you'll never really know if you have a good model if you overfit it. Leave some data aside that you only look at the end. Right? So the learning algorithm does not have access to this data. But then you can evaluate what it did on this data. So here's what happened. As you grow the tree, first the accuracy goes up, and then it plateaus, and then look at this. It starts to go down and down and down and down. Big problem. You thought you were here, but in reality, you were here. Where should you have stopped growing the decision tree? Assuming you can read these numbers.
20.
At 20, right? Or somewhere between 10 and 20, right? Actually, I would stop at 10 because given two equally accurate, decision trees, I'd rather take the smaller one. But as far as overfitting goes, yes, anything between 20 and 20 would have been okay. But after that, my improvements are an illusion. Okay? This is the overfitting problem. Is you think you're doing better and better, but you're actually doing worse and worse. And the shape of these curves, learning curves, which is what these are called, come in all shapes and sizes. But this is actually very typical, which is, not coincidentally why it's on this slide. Notice that initially your accuracy gets better very quickly. Right? This is your big win. You still have a simple decision tree and it's already predicting quite well. But you want to predict even better. And then things plateau. And then what you get is this region where you think you're getting slowly better, but you're actually getting slowly worse and worse and worse and worse. Okay? So, moral of the story. I want to stop here. How do I do that? I need to figure out where to stop without looking at the holdout data because I don't have it. Right? So how do I do that? Now this seems hard, right? But the good news is actually precisely because this early part of the curve is steep and this one is kind of gradual, you have a lot of leeway, right? You could stop anywhere between 10 and 20, and actually those are all fine. But if you stop at 30, sure, you didn't quite get to the 75%, but it's still whatever, 73, 74, not the end of the world, right? So you don't necessarily need to nail down the exact point at which overfitting begins. But you would better do some overfitting avoidance, or you could get a disaster like the speech synthesis one that I just talked about. Okay? Questions? So